Hello! In this video, we're going to take a look at one more topic related to water, and that is that water dissociates. It falls apart at low rates. So here's a picture of two water molecules, and sometimes they interact with each other in a way such that one water molecule picks up an extra proton, that's a hydrogen ion. The other water molecule loses that hydrogen ion or that proton. And so we would say water dissociates or falls apart. Sometimes we write it like this. I'm going to go ahead and write this dissociation in a slightly different way. What if we have one water molecule? Sometimes we write it like this, that one water molecule can fall apart into protons or hydrogen ions plus hydroxide ions, the oxygen and hydrogen that carry that negative charge. This happens in pure water. You'll have some protons and some hydroxide ions. And in pure water, the concentration of protons, that's what these brackets mean, right, is equal to the concentration of hydroxide ions, and that equals a very small number, 10 to the negative 7th molarity. In other words, if you're looking at a liter of water, there's 1/10,000,000th of a mole of protons in that liter of water. Okay, a small amount. So who cares? Why is this important for life? Well, it turns out that if other substances are dissolved in water, then the concentrations of protons and hydroxide ions can change. And then you get things like acids and bases. And that can be really important for life on Earth. So when there are substances that are added to water that increase the concentration of protons in solution, so you can write the word increase there, you have an acid. So acids are materials that are substances that increase the concentration of protons in solution. They make the solution more acidic, we might say, right? Hydrochloric acid is a powerful, a strong acid, we say, that dissolves into its components, increasing proton concentrations in solution, and you've got something very acidic. Bases are substances that decrease the proton concentration in some way. So they're the opposite. We might talk about a solution as being basic, right? Sodium hydroxide is a very strong base that completely dissociates into sodium ions, but also hydroxide ions. How does sodium hydroxide decrease the proton concentration in water? Well, remember, when we think about water, we have to remember that some molecules of water have fallen apart, right? It goes the other way. When sodium hydroxide is put into a solution of pure water, these hydroxide ions, I sometimes do that, react with protons, removing or decreasing the concentration of protons in solution. So that's what bases do. So how do we measure how acidic or basic a solution is? We use the pH scale. You're probably familiar with that. And then our next question here is, why is that important? Okay, here's a pH scale. You have to look at it for a minute. The pH scale ranges from 0 to 14. It's a logarithmic scale. And we can calculate for any substance the pH of a substance as equal to negative log of the concentration of protons in that substance. All right? So in pure water, the concentration of protons is 10 to the negative 7th molarity. If we stick in 10 to the negative 7th into our formula, negative log of 10 to the negative 7th, we get negative 7, or we get 7. Pure water has a pH of 7. If we change that concentration of protons, then we change the pH. Notice that A pH that's smaller than 7 we would say is more and more acidic. A pH bigger than 7 is more and more basic because, and we'll take a look at this, how this works. So let's look at something like coffee. Here sits coffee at about a pH of 5. What's the concentration of protons in coffee? Well, you can work backward, or you can kind of, use our example of water to sort this out. The concentration of protons if the pH is 5, is equal to negative log of this concentration of protons, right? Do the math, and you realize, oh, that's 1 times 10 to the negative 5th molarity. Okay? Coffee has more protons, has a higher concentration of protons than water. It's acidic. 1 times 10 to the negative 5th molarity is bigger than 1 times 10 to the negative 7th. In fact, how many times bigger is it? That's our question here. Its proton concentration is how many times that of pure water. Well, we're moving on the pH scale from 7 to 5, but remember this is a logarithmic scale. Every step, every increment in the pH scale represents a 10-fold change in proton concentration. So here we've got 10 times 10, or 100 times the concentration of protons in coffee is 100 times more. So 100 times, you're going to have to write more than that of pure water. Right? That's B. Yes. All right. So why is this important for life on Earth? That's really the important question we want to know. Why is it so important? Well, it turns out that chemical reactions happen in a very narrow range of pHs. Okay? So, for example, if we look at our blood has a pH, I have to look it up here, of between 7.35 and 7.45. If our blood becomes more acidic or more basic than that little tiny range, we're dead. That's not good. Lots and lots of chemical reactions take place in very narrow ranges of pHs, or narrow ranges. And so the acidity or the basicity, the pH of a solution is critical then for life on Earth. All right. There is one example that our textbook uses, the acidification of oceans, how oceans are becoming more acidic and how that's damaging life in the oceans, particularly the reef organisms that build the reefs, because there are more protons in solution in the water. There's less skeletal materials for these organisms to build their skeletons, to become reef animals. So it's a pretty important thing that the oceans are becoming more acidified, and it's something that we need to worry about. That's the end of Chapter 3 on water. Here are some ways to review, and that's it for now. Thanks.